Right. So towards the end of our last class on three-dimensional geometry, I introduced some basic equations of straight line and plane, both in Cartesian format and in vector format, right? I'll make a few more remarks on both straight lines and planes in the class today, right? Now, first of all, recall this was a straight line in Cartesian format. X minus x1 by L is y minus y1 by m is z minus z1 by n. Li plus mj plus nk is a unit vector parallel to the line. L, m, n are referred to as direction cosines of the line, right? And there is a point P not lying on the line. There is a point P not lying on the line. And let's say its coordinates are alpha, beta, gamma. Its coordinates are alpha, beta, gamma. F, let's say, is the foot of the perpendicular from the point P onto the line. F is the foot of the perpendicular from the point P onto the line. Now this F lies on this line. So the coordinates of this F, x, y, z, will be such that it will be satisfying this condition. Let's say for the x, y, z of F, each of these ratios is R. For x, y, z of F, let's say these ratios is R, right? So the x of the point F is going to be x1 plus LR, y of the point F is going to be y1 plus MR, z is going to be z1 plus NR. So the coordinates of F would be x1 plus LR, y1 plus MR, z1 plus NR. These would be the coordinates of the point F, right? Now, a unit vector along the line evidently is Li plus Mj plus Nk. Is a unit vector along the line, right? Now, you have the coordinates of the point P. So, the position vector of the point P is what? Alpha I plus beta j plus gamma k. That's the position vector of the point P. The position vector of F is going to be x1 plus Lr I cap, y1 plus Mr j cap, and z1 plus Nr k cap. That would be the position vector of F, which means, let's say, a vector in this direction. That means the vector Pf, the vector Pf is going to be x1 plus Lr minus alpha I cap, y1 plus Mr minus beta j cap, z1 plus Nr minus gamma k cap, right? That is the Pf, the vector Pf would be position vector of F minus position vector of P. So then the vector Pf is x1 plus Lr minus alpha I cap, y1 plus Mr minus beta j cap, z1 plus Nr minus gamma k cap, right? Now, so far we have not used the fact that Pf is perpendicular to the line. If Pf is perpendicular to the line, it's perpendicular to Li plus Mj plus Nk. That means Pf dot Li plus Mj plus Nk must be 0. So, using the fact that Pf dot Li plus Mj plus Nk is 0, that means this vector dot Li plus Mj plus Nk, that's 0, which gives me like a x1 plus Lr minus alpha into L plus y1 plus Mr minus beta into M plus z1 plus Nr minus gamma into N. That's equal to 0. And this gives me the value of R, because this is like a R into L squared plus M squared plus N squared, which is simply R. And then the rest of the terms, x minus alpha into L goes on the other side, y1 minus beta into M goes there, z1 minus gamma into N goes on the other side, giving you the value of R. You know the value of R from this equation. And once you know the value of R, which represents the foot of the perpendicular from P onto the straight line, then the x, y, and z coordinates of the point F would be available. The x, y, z coordinates of the point F would be available. And once you have that in place, then obviously the length PF can be found. The foot of the perpendicular is known. You could also find the image of the point P with respect to the line, alpha, beta, gamma. And let's say the image of the point P with respect to the line is I. Call it alpha prime, beta prime, gamma prime. And this is the point F. Then obviously F being the midpoint of Pi, alpha plus alpha prime by 2 must be x of F. X of F, which we have already known because R has been computed. X of F would be alpha plus alpha prime by 2. Y, similarly, Y of F is going to be beta plus beta prime by 2. And Z of F is going to be gamma plus gamma prime by 2, etc. Right? So you would also know the image of the point P with respect to the line once you've obtained the value of R from this dot product, Clear? So given a line and given a point not on the line, you can find the foot of the perpendicular from the point P onto the line. You can also find the image of the point P with respect to the line, and so on. And the length PF can be found from this vector mod of PF, which would be root this square plus this square plus this square. That's going to be the length PF, the perpendicular distance of P from the line. Clear? Now, in the same thing in vector format. Suppose you have a line whose equation is R equal to A plus lambda B. This is the vector equation of a line where what is A? A is the position vector of a certain known point on the line. A is the position vector of a certain known point on the line. What is B? B is a vector parallel to the line. B is a vector parallel to the line, right? Lambda is a parameter. If you plug in various values of lambda, you will get position vectors of different points lying upon the line. Clear? So that's the equation of a line governed by two entities. A, the position vector of a certain point on the line. B, a vector parallel to the line. And you have a certain point P. Let's say, whose position vector is R0. And you want to be able to find the foot of the perpendicular from the point P onto the line. That means the position vector of F. You want to be able to find the position vector of F, which is the foot of the perpendicular from the point P onto the line. Now, the position vector of F, R, must satisfy this equation for lambda equal to some lambda naught. Some lambda equal to lambda naught will give you the position vector of F. Yes or no? Some lambda. No, you didn't understand this, now. I'm saying this is the position vector of various points on the line. Why various points on the line? Because for different lambdas, you will get different points on the line, R of different points on the line. Now, for the point F, which is on the line, lambda equal to lambda naught, let's say, will give you the position vector of F. So the position vector of F would be of the form some A plus lambda naught B. Where we do not know lambda naught, we will be able to find lambda naught. B is a vector parallel to the line. What's the vector PF? The vector PF is position vector of F minus position vector of P, which is A plus lambda naught B minus R naught. That's a vector PF. How do you find lambda naught? From the fact that PF is perpendicular to B. That means PF dot B must be 0. PF dot B must be 0. That means A plus lambda naught B minus R naught dot B must be 0, right? Which means lambda naught b dot b would be lambda naught mod b squared. We need to find lambda naught, because if I know lambda naught, I know the position vector of f. My objective is to find lambda naught. So now lambda naught into b dot b is lambda naught mod b squared. And then a minus r naught dot b goes on the other side to give me like a r naught minus a dot b is what I get. When a naught minus r naught, a minus r naught is transposed on the other side, it gives me r naught minus a dot b. So then lambda naught is known to me. Dot b by mod b squared. And once you know lambda naught, you know the position vector of f. Once you know the position vector of f, then the vector pf can be found. The vector pf and mod of pf will give me the length pf. Mod of pf will give me the length pf, and the image of the point p with respect to the line. Let's say this is r naught. Its image is, let's say, r naught prime is its image. Is its image of p with respect to the line. And you already know the position vector of f. Position vector of f is like a plus lambda naught b, where we have already obtained the value of lambda naught. Evidently then r naught plus r naught prime by 2 must be rf, right? So rf is r naught plus r naught prime by 2. So r naught prime can be obtained, the position vector of the image of this point p with respect to the line itself. Clear? Now suppose I am given two parallel lines . Two parallel lines. Let's say one line is r equal to a1 plus lambda b. This is a line that passes through a point whose position vector is a1 and is parallel to b. Let's say this is another line r which passes through a point whose position vector is a2 and is parallel to b. And lambda is a parameter, so don't think that this lambda is the same as that lambda. It's like you can assign different values to lambda to get position vectors of various points in the line. And you want to find the separation between these two lines. You want to find the separation between these two lines. Realize that there is a point P on the line whose position vector is a1. There is a point Q on the line, on this line, whose position vector is a2. And both these lines are, let's say, parallel to the vector P, are parallel to the vector P. Both these lines are parallel to the vector P. Now, this is the vector QP. This is P. This angle is theta. QP dot B. Look at QP dot B. What is QP? The vector QP is A1 minus A2. A1 minus A2 will be the vector QP, final position minus initial position. Dot B. That's equal to mod QP into mod B into sin theta. Mod QP into mod B into sin theta by definition. I'm sorry, cos theta. I'm so sorry. Cos theta. Actually, I want this distance. So I would rather want to take the cross product because this is QP sin theta. So if I took like a QP cross B, then what's that going to be? Mod QP into mod B into sin theta. Mod QP into mod B into sin theta. But mod qp sin theta is this distance d. Mod qp sin theta is this distance d. Yes or no? The required distance between the two lines. This length is mod qp and this distance is mod qp sin theta, as you can see, right? So mod qp sin theta is d into the vector b. That's qp cross b. Qp cross b is what? Qp, as you can see, is a1 minus a2 cross b. Mod of this dot cross product is going to be magnitude of qp into magnitude of b into sin theta by definition. So mod of this is g into b, g into mod b. So then d is obtained as mod a1 minus a2 cross b divided by mod b, That's the separation between two parallel lines. That's the separation between two parallel lines, each parallel to a vector b, and a1 being the position vector of one point on one line, a2 being the position vector of one point on the other line, and b is a vector parallel to both the lines. Then the separation between the two parallel lines is given by this expression. This is sometimes used. Okay. Two lines in general would be like this. They would be non-parallel, non-intersecting, non-parallel, non-intersecting. Right? If two lines are like this, oriented in space, they are non-parallel, non-intersecting, non-parallel, non-intersecting. And two lines that are non-parallel, non-intersecting are referred to as skew lines, One more thing, if this is a point A and this is a point B, and this is a certain direction D, then the perpendicular from A onto B, call it P, the perpendicular from B onto this direction D, call it Q, then PQ is said to be the projection of AB along D. PQ is said to be the projection of AB along, which means what? Which really means that, if there was, let's say, a solid stick AB, and this was a certain line, and if you threw light on AB, then the shadow of AB will be this PQ. Shadow of AB on this will be PQ, right? That's when we say that PQ is the projection of AB along D. PQ is said to be the projection of AB along D. Now, evidently, PQ is the same as this length. This length is also PQ. And let's say a unit vector parallel to D is D cap. Let's say a unit vector parallel to D is D cap. Then the projection of AB along D, along the direction D, suppose this angle is alpha, is AB cos alpha, yes or no? Which could also be the vector AB dot a unit vector D cap, yes or no? A unit vector in this direction, what's AB dot D cap? Will be magnitude of AB into magnitude of D cap, which is 1 into cos alpha. नहीं समझे क्या? AB dot d cap is magnitude of AB into magnitude of d cap, which is 1, into cos alpha, cosine of the angle between AB and d cap. So it could be written as AB dot d cap, which is the same as PQ, which is the same as PQ, right? This length, which is AB cos alpha, is the same as PQ. So given AB, if you want to find the projection of AB in a direction D along which a unit vector is d cap, then all that you need to do is do a AB dot d cap or its magnitude, AB dot d cap or its magnitude, right? I mean, if this turns out to be a negative number, then take its magnitude, take its modulus. So that's the projection of AB in a given direction. And how do you obtain that projection? From A, drop a perpendicular in that direction. From B, drop a perpendicular in that direction. You get the projection of AB along D. You get the projection of AB along D. Suppose I'm given two skew lines. Like I said, in general, two non-parallel, non-intersecting lines in space, they are referred to as skew lines. Right? I mean, in fact, they intersect. If if two lines intersect, they are only a special case of skew lines. You say, right? Or if they are parallel, then also we say they are special cases of skew lines. But in a very general sense, I would refer to skew lines as two non-parallel, non-intersecting lines. They are skew lines. These are two skew lines. I mean, they seem like belonging to the same plane, but that's not the case. It's like one could be here. I mean, that's how I will have them represented the plane. They're like this. It's like this line is the shadow of this on the board, and this one is the shadow of this line on the board. They're like representatives of the same thing. But in general, they could be like out of plane with each other, right? In general, that's the way it is. But for the sake of the limitation that we have on the board, this is how I represent. But they are skew lines in general like this, right? These are two skew lines. Don't think that they intersect. I mean, because one is, let's say, slightly raised, for example, right? So they don't seem to intersect. They will bypass each other. In Cartesian format, let's say this line is x minus x1 by L1, is y minus y1 by M1, is z minus z1 by N1 is this line. What does this mean? It means that this line passes through a point whose coordinates are x1, y1, z1, and a unit vector along this line is like a L1 I cap plus M1 j cap plus N1 a cap. That's what this means. Huh? Let's say there is another line which is x minus x2 by L2, is y minus y2 by M2, is z minus z2 by N2. So this represents a line passing through a point whose coordinates are x2, y2, z2, and this line is parallel to a unit vector L2i plus M2j plus N2k. So there is a point P on the line whose coordinates are x1, y1, z1. There is a point Q on this line whose coordinates are x2, y2, z2. And I want to be able to find the shortest distance between the two lines. I want to be able to find the shortest distance between the two lines. These are two skew lines. If I select one point on this line and another point on this line, the distance between them would be different for different pairs of selection on the two lines. For different pairs of selection on the two lines, I now want to be able to find the smallest distance between the two lines, the shortest distance between the two lines. One thing conceptually, just hold these two pens like this. In general, if I select a certain fixed point on this line, then different points on this line will be at different distances, right? But for this fixed point on this line, the shortest distance can be obtained when I take this point and drop a perpendicular onto this line, right? The other thing now, on this line I can select various points. Let me select one particular point. From this point I can have various distances from this line, but again the shortest distance would be when I take this point and drop a perpendicular onto this line, right? Which means in general, if I combine both these effects, the segment of shortest distance between the two lines, would be perpendicular to this line as well as perpendicular to this line. Yes or no? The shortest distance between the two lines would be a segment perpendicular to this line as well as perpendicular to the other line. That's going to be the shortest distance between the two lines. Any departure from that will cause a segment larger than this, right? So this fact you understand? The segment, yeah, please. Thanks. The shortest segment between the two lines is a segment which is perpendicular to both the lines. This fact is clear? Let's say this is a segment which is perpendicular to both the lines. This is a segment which is perpendicular to both the lines. Call it GH, which is the segment of shortest distance between the two lines, and evidently this segment will be perpendicular to this line as well as perpendicular to this line in the skew pair. Clear? Now, let's say this GH is part of a line. This GH, the segment of shortest distance, is part of a line which is, say, x minus alpha by L is y minus beta by m is z minus gamma by n. Let's say GH belongs to a line whose equation is x minus alpha by L, y minus beta by m, and z minus gamma by n. That means this line of which GH is a part passes through a point alpha, beta, gamma and is parallel to the vector Li plus Mj plus Nk. Yes or no? I want to be able to find this length. The segment of shortest distance between the two lines. Now, do you realize GH has a certain direction? GH is like a certain direction. For that direction, for this direction, call it D. This direction is D. From G is the foot of the perpendicular from P onto the direction D. Yes or no? G is the foot of the perpendicular from P along this direction, because PG is perpendicular to D, right? Yes or no? Similarly, QH is perpendicular to D, so H must be the foot of the perpendicular from Q onto the direction D. H must be the foot of the perpendicular from Q onto the direction D. Which means, can I not say that GH, like we discussed a little while ago, GH must be the projection of PQ along D. GH, the length GH must be the projection of P along D. Yes or no? I mean, think of this as a certain line. If you throw light here, then along this direction, the projection of PQ will be this. The shadow of PQ will be GH. Yes or no? GH is the projection of PQ along the direction D. What direction D? A unit vector in this direction is like a Li plus Mj plus n cap. GH is the projection of PQ along the direction Li plus Mj plus N cap. So can I not say that, let's say PQ, this is PQ, dot a unit vector in this direction will give me GH. The projection of PQ in a given direction can be obtained by saying PQ dot a unit vector in this direction, PQ dot a unit vector in that direction, or its magnitude, So this is like PQ dot a unit vector in this direction, which is like a Li plus Mj plus Nk. Right? That's GH. That's GH. That's the length GH. Yes or no? Where what's PQ? PQ is x2 minus x1 I cap plus y2 minus y1 j cap plus z2 minus z1 k cap. That's PQ, right? That's PQ. That's PQ. That's GH. Sorry, that's GH. PQ dot this. That's GH. Now we need to find L, M, and N. We need to find L, M, and N. How do you find L, M, and N? See, x1, x2, y1, y2, z1, z2 are known, but L, M, and N we just pretended we knew. I mean, we just assumed that the line of shortest distance has direction cosines Li, L, M, and N and pass through a certain point, alpha, beta, and gamma. Very clearly, a unit vector in this direction will be perpendicular to a unit vector in this direction. Yes or no? A unit vector in this direction along GH is Li plus Mj plus Nk, whereas a unit vector in this direction is L1i plus M1j plus N1k. The dot product of these two unit vectors must be 0. That means LL1 plus MM1 plus NN1 must be 0. Li plus Mj plus Nk dot L1i plus M1j plus N1k is 0, implying therefore that LL1 plus MM1 plus NN1 must be 0. Right? And not only that, this Li plus Mj plus Nk must be perpendicular to a unit vector in this direction. A unit vector in this direction is like L2i plus M2j plus N2k, which must be perpendicular to Li plus Mj plus Nk. The dot product 0 means LL2 plus MM2 plus NN2 must be 0. Right? From these two equations, I can apply the rule of cross multiplication. If I apply the rule of cross multiplication, then L by M1 N2 minus M2 N1 is minus M by L1 N2 minus L2 N1 is N by L1 M2 minus L2 M1. Yes or no? This is what you get when you apply. I hope all of you know this. We did this in quadratic equations. The rule of cross multiplication, this is what you get. And if this is the case, then each can be written as square root of this square plus this square plus this square divided by this square plus this square plus this square. Remember that. Each can be written as square root of L squared plus minus m whole squared plus n whole square divided by root this square plus this square plus this square, isn't it? So, but the numerator root L squared plus m squared plus n squared is 1 because Li plus Mj plus Nk we assumed is a unit vector along the segment GH, along the segment GH. So, this is like 1 by root summation of terms of the following kind m1 n2 minus m2 n1 whole square kind of a term. Root this square plus this square plus this square means all the, there are 3 pairs out of L, M and N, there are 3 pairs. This is like a Mn pair, there is a Ln pair, there is a Lm pair with the subscripts interchanged. That's what constitutes this summation. So, this will give me the value of L, the value of M and the value of N, which we didn't know. In our computation of GH, we arrived at x2 minus x1 L plus y2 minus 5n M plus z2 minus z1 N. L, M, N were not known to us, but now they are known to us. We can plug in these values of L, M and N from this equation into the expression for GH. GH would either be that expression or its magnitude based on the sign. So, once you plug in the value of L, M and N in the expression GH, which would either be x2 minus x1 L plus y2 minus y1 M plus z2 minus z1 N or its magnitude, it will turn out that this expression will be actually the following determinant, it will be the determinant x2 minus x1, y2 minus y1, z2 minus z1, L1 M1 N1, L2 M2 N2, the whole divided by square root of summation M1 N2 minus M2 N1 whole squared. This is what it will turn out to be. You might want to remember this result then. So, given 2 lines, this is the segment, this will represent the right. Now, as a special case, if the shortest distance between the 2 lines becomes 0, then the 2 lines obviously intersect. What it means is that the 2 lines intersect. The moment 2 lines intersect, they would constitute a plane. The moment 2 lines intersect, they would constitute a plane. Very easy to see that. If these are 2 lines, if they happen to intersect, then they would lie on the same plane. They would be coplanar lines. They would then be coplanar lines. For sure, if 2 lines intersect, they would be coplanar lines. They would be coplanar lines because these are two lines and they happen to intersect at a point, this, right? Which means what? If there is a vector b1 along this line and there is a vector b2 along this line, then a normal to the plane containing the two lines will be a b1 cross b2. We can think of a plane constituted by these two lines such that the normal to the plane constituted out of this is going to be b1 cross b2. If b1 is a vector parallel to this line, b2 is a vector parallel to this line, then b1 cross b2 would be perpendicular to both the lines and will therefore be a vector normal to the plane containing b1 and, right? So if two lines intersect, that means if GH is 0, then the two lines have to be coplanar. If GH is 0, the lines ought to be coplanar. If GH is 0, lines are coplanar. In fact, this then, which means if x2 minus x1, y2 minus y1, z2 minus z1, L1 m1 n1, L2 m2 n2, if this is 0, then the two lines will be coplanar. This then brings us the condition for coplanarity of two lines, this and this. The direction cosines are these, and one line passes through x1 y1 z1, the other line passes through x2 y2 z2. L1 m1 n1 direction cosines of one line, L2 m2 n2 direction cosines of the other lines. The two lines will then turn out to be coplanar lines, right? This is important. So this is as far as the coplanarity related to two skew lines is concerned. Shortest distance 0 in Cartesian format. In Cartesian format, this condition, right? Let's arrive at a similar condition in vector format. Given the vector equation of two lines, we want to figure out the segment of shortest distance between the two lines and consequently the condition for coplanarity of two lines. Condition for coplanarity of two lines in the event they are. Can I wipe this off? Let's now, essentially it's the same thing. You know, I don't even want to distinguish between the two formats. It's just the ornamental looks that are different, but deep down they owe a common origin. So it's only for the sake of representation that we have two formats, but in principle they really talk of the same thing all the time. So in vector format, again, let's look at two skew lines. In vector form, let's say this line is r equal to a1 plus lambda b1. What does this mean? It's a line passing through a point whose position vector is a1 and is parallel to the vector b1. This is another line r equal to a2 plus lambda b2. This is a line which passes, whose position vector of various points is obtained from the following, where a2 is the position vector of any point on the line, of a certain fixed point on the line, and b2 is a vector parallel to the line. Then this will give you, for different values of lambda, position vector of different points on the line, right? This is the vector representation of whole line. Again, principally, this is P, a certain point whose position vector is a1. This is Q, a certain point whose position vector is a2, right? And the segment of shortest distance between the two lines is going to be perpendicular to both the lines, The segment of shortest distance is going to be perpendicular to both the lines, yes or no? Right. Now, GH, bless you, GH is perpendicular to this line as well as this line. That means GH is perpendicular to the vector B1 and is also perpendicular to the vector B2, right? So that means a vector parallel to GH is B1 cross B2, because B1 cross B2 is perpendicular to both B1 and B2, yes or no? B1 cross B2 is perpendicular to both B1 and B2. So B1 cross B2 lies along GH. B1 cross B2 is a vector parallel to GH, yes or no? That means a unit vector parallel to GH, a unit vector parallel to GH is B1 cross B2 divided by mod B1 cross B2. That will be a unit vector parallel to GH. That will be a unit vector parallel to GH, yes, right? And again, what is GH? It's a projection. It's a projection of PQ along n cap. GH is the projection of PQ along n cap. That means GH can be written as PQ dot n cap. Projection of PQ in a given direction is PQ dot a unit vector in that direction. Or its magnitude, if it turns out to be negative, its magnitude, that's GH. Where what's PQ? PQ is A2 minus A1 dot n cap. N cap is B1 cross B2 divided by mod B1 cross B2. This is the shortest distance between two lines, r equal to A1 plus lambda B1 and r equal to A2 plus lambda B2. This will represent the shortest distance between the two lines. And in the event this GH is 0, then the two lines would intersect and will be rendered coplanar. If two lines intersect, they ought to be coplanar. If two lines intersect, they ought to be coplanar, right? So if GH is 0, lines intersect, or they then become coplanar, or then they become coplanar. Coplanar means this would imply GH equal to 0 would imply A2 minus A1 dot B1 cross B2 equal to 0. The numerator of this equal to 0. Both in Cartesian format and in vector format, we've successfully arrived at the expression for the segment of shortest distance between the two lines, and consequently the condition for coplanarity, which happens when that shortest distance is 0, that is when the two lines intersect. It then becomes our responsibility to put across, if they intersect, that means if they are coplanar, the equation of the plane containing the two lines. In the event they are coplanar. In the event you figure out that the two lines are coplanar, then the onus is on you to find out the equation of the plane containing the two lines. Yes or no? If the two lines turn out to be coplanar, which you can check from one or the other condition in Cartesian or vector format, then the equation of the plane, both in Cartesian and vector format, needs to be worked out. Equation of the plane containing the two lines, right? Common plane between the two lines. So we then venture into the same. Can I write this off? Let's say we have two lines, x minus x1 by L1 . This is line L1, this is a line L2, we can check whether these lines are coplanar or not. The check is when the determinant x2 minus x1, y2 minus y1, z2 minus z1, l1, m1, n1, l2, m2, n2 is 0. That is when the two lines intersect, then they would be coplanar. In the event they intersect, that means in the event that condition is satisfied, there exists a common plane containing the two lines. We now want to be able to find the equation of the required plane. We now want to be able to find the equation of the required plane. Now one thing, the plane containing L1, for example, will obviously pass through x1, y1, z1. Will always pass through x1, y1, z1. And let's say a normal to the plane is ai plus bj plus ck, as was the convention, right? Let's say a normal to the plane was ai plus bj plus ck. Then the equation of the plane passing through x1, y1, z1, for example, equation of a plane passing through x1, y1, z1 and having ai plus bj plus ck as its normal is a into x minus x1 plus b into y minus y1 plus c into z minus z1 equal to 0, isn't it? Ax plus by plus cz means ai plus bj plus ck is a normal to the plane. This certainly is a plane because it's of the form ax plus by plus cz plus some d equal to 0. So it's the equation of a plane, right? You were not there in my last class. So what was the equation of a plane? Ax plus by plus cz plus d equal to 0, where ai plus bj plus ck is a normal to the plane. See, that is what it is, ax plus by plus cz, and minus ax1 minus by1 minus cz1 is a d. So is it not of the form ax? So is it not a plane? Is the normal to the plane not ai plus bj plus ck? Right? Does this plane not pass through x1, y1, z1? x1, y1, z1 satisfies this equation. So it's a point on this plane. So it's a plane passing through x1, y1, z1 and having normal as ai plus bj plus ck. Clear? So for sure, the plane that we are seeking will be of this form. X, y, z would be different points on the required plane, on the required plane, where we are only pretending that we know ABC. The job then is to be able to dump ABC out of the scene, right? The plane obviously also contains L2, the line L2 also lies on this plane. So the point x2, y2, z2 also lies on the plane. The point x2, y2, z2 also lies upon the plane. That means in this, if you put x equal to x2, y equal to y2, z equal to z2, this condition would be met, right? We are seeking a plane containing both L1, L2, L1 and L2. So it will pass through both x1, y1, z1 and x2, y2, z2. For its passage through x2, y2, z2, we must have the following condition met: x2 minus x1, now look, this was the plane, and a normal to the plane was like a ai plus bj plus ck. It was a normal to the plane, right? The line L1 was lying on the plane. That means L1i plus m1j plus n1k is parallel to the plane, right? The vector L1i plus m1j plus n1k is along the plane, and ai plus bj plus ck is normal to the plane, whereas this L1i plus m1j plus n1k, since it's parallel to the line, it's parallel to the plane, right? That means ai plus bj plus ck must be perpendicular to L1i plus m1j plus n1k. A normal to the plane will also be perpendicular to L1. A normal to the plane will always be perpendicular to any line L1 lying on the plane, isn't it? So if there is a certain vector parallel to the line, then it will be perpendicular to AI plus BJ plus CK, which is a normal to the plane. Yes or no? So if these two vectors are perpendicular to each other, then AL1 plus BM1 plus CN1 must be 0. Their dot product must be 0. This dot this must be 0, right? Clear? Similarly, the line L2 also lies on the plane. So the vector L2I plus M2J plus N2K is also parallel to the plane. AI plus BJ plus CK is perpendicular to the plane. So AI plus BJ plus CK must also be perpendicular to L2I plus M2J plus N2K. Therefore, the dot product of AI plus BJ plus CK and L2I plus M2J plus N2K must be 0. So then the dot product 0 means AL2 plus right. Now we need to this is the equation that we are seeking. This is the equation of the plane where ABC would have to be gotten rid of. Now to get rid of ABC, equation 1, 3 and 4, use equations 1, 3 and 4 where you can eliminate ABC, using 1, 3 and 4. When you eliminate ABC, you get the following determinant. X minus x1, y minus y1, z minus z1, L1 m1 n1, L2 m2 n2. This must be 0. Where what does x, y, z represent? Any point on the plane, Therefore, when you simplify this, you get the equation of the plane containing the two lines. That is, provided the two lines are coplanar, which is provided that GH is 0. Then you can directly say that this must be the equation of the plane containing the two lines. This must be the equation of the plane containing the two lines. Yes or no? Right? In fact, if you used 2, 3 and 4 to eliminate ABC, you will get the condition for coplanarity. If you used equations 2, 3 and 4 to eliminate ABC, you will get the determinant x2 minus x1, y2 minus y1, z2 minus z1, L1 m1 n1, L2 m2 n2 equal to 0, which is the condition for coplanarity of the two lines. I didn't do that again because we've already done that from independent equations. So I didn't use 2 again. But then if I had not done what I did a little while ago, then I would have used 2, 3, 4 to arrive at the condition for coplanarity by eliminating ABC, which would give me like a x2 minus x1, y2 minus y1, z2 minus z1, L1 m1 n1, L2 m2 n2 equal to 0, etc. Right? But then this, if 2, 3, 4 are met, then this would be the equation of the required plane. Containing the two lines. Clear? And now the same thing in vector notation. So line L1, which is R equal to A1 plus lambda B1, L2, which is R equal to and I've already told you the condition that these two lines become coplanar. For their coplanarity, the condition with which compliance must be drawn is A2 minus A1 dot B1 cross B2. This must be 0. This is the condition for coplanarity of the two lines, right? And once this is established, then there is a common plane containing the two lines. There is a common plane containing the two lines. So these are the two lines. If they are coplanar, they would have intersected, and that happens when this condition is met. Now, obviously the plane will contain these two lines. This line is parallel to a vector B1, this line is parallel to a vector. So the required plane will have its normal B1 cross B2. B1 cross B2 will be a normal to the plane, yes or no? If this is B1, this is B2, then there is a common plane containing the two lines, and a normal to the plane is going to be B1 cross B2. Now if R be the position vector of any point, let's say on the plane, R be the position vector of any point on the plane, A1 is the position vector of a certain point already known on the plane, then R minus A1 must lie on the plane. If R is the position vector of a certain point on the plane, any point on the plane, A1 is the position vector of a certain point already known on the plane. So R minus A1 must lie on the plane, and therefore R minus A1 must be perpendicular to B1 cross B2. R minus A1 must be perpendicular to B1 cross B2. That means R minus A1 dot B1 cross B2 must be shunya. So if this condition is met, and if R is the position vector of any point in the plane, then R minus A1 dot B1 cross B2 must be 0, or R dot B1 cross B2 must be A1 dot B1 cross B2, which is like R dot, a normal to the plane, is a constant scalar. This is a scalar because this is a vector, dot a vector will give me a scalar. This is like my D, R dot n cap, n equal to D. So which represents the equation of the common plane. Equation of the common plane, R dot B1 cross B2 is A1 dot B1 cross B2 is the equation of the common plane. Now I know that the common plane exists. That's why I could find the equation of the common plane, because this condition is met. Right? For today, I'm not fit enough to last longer than this.